Hello, my name is Ruben Duarte, I'm a geographer and GIS specialist by profession, and in today's video I'm going to show you an interesting methodology for creating flood risk maps based on a scientific article. Flood risk mapping using GIS and multi-criteria analysis, a Greater Toronto Area case study. This article, published in 2018, was written by Dr. Daniela Rincón and Dr. Usman T from the Department of Civil Engineering, Lassonde School of Engineering, York University, Toronto, and by Dr. Costas Armenakis from Geomatics Engineering, Department of Earth and Space Science and Engineering, Lassonde School of Engineering, York University, Toronto as well. The article focuses on the analysis of 4 risk scenarios using different variables for a study area located at the intersection between the Greater Toronto Area and the Don River watershed, along with the rain gauges. It begins by explaining the reasoning behind the choice of certain variables, which are slope, height above the nearest drainage, distance to streams, curve number, total and effective precipitation, and the floodplain. In this video, I'll show you how to calculate 6 of these 7 variables, since the floodplain I'll be using in this video was already previously calculated. After calculating these elements, I'll proceed to reclassify each one based on table 2 of the article. Next, 4 hazard scenarios will be calculated based on figure 5, where different variables are used with different weights, calculated using the analytic hierarchy process method. A simple calculation of social vulnerability will also be carried out, and finally a combination of hazard and vulnerability will be made, resulting in 4 risk maps. This video was truly enjoyable to make. I personally learned a lot from it, and I hope you enjoy it and that you can learn something new and apply to your work, whether at the professional level or for school or university projects. Without further delay, let's dive into the video. As I mentioned in the introduction of this video, the article I have on the screen will serve as the foundation for this tutorial. In the case of this article, Flood Risk Mapping using GIS and Multi-Criteria Analysis, a Greater Toronto Area study, the study area is the city of Toronto in Canada. However, in this video we will apply the same methodology to a different area, specifically a selected area located in Aveiro, Portugal. Initially, we will construct several elements that will form the basis of the hazard map, where we will create variables such as slope, the height above the nearest drainage, the S, which means the distance to streams, curve number, total precipitation, effective precipitation, and also we are going to use the floodplain. After calculating all the previously mentioned elements, we will define 4 scenarios. Each scenario will be based on a selection of the created elements, with each one assigned a different weight. After this, we will also calculate the vulnerability, which combined with the hazard scenarios will give rise to the final risk maps. Later in this article, there is an explanation of how the weights for each variable are determined. If you like to learn more about this topic, I have a video on the channel entirely dedicated to it. The link to that video is now appearing in the top right corner of the screen. Moving on to ArcGIS Pro, for this tutorial we will only need 6 space datasets: the DEM, which refers to elevation, land cover, where we have the following types, soil hydrologic groups. Later on we will need to correct these white gaps, and I will also show you one of the ways we can address this issue. We will also need the floodplain data, the census data, which will be used in the vulnerability analysis. In my case, the most recent data available is from 2021. And finally, we have this table with several meteorological stations and precipitation data in millimeters from 2000 to 2025, which will be used to calculate both the total precipitation and also the effective precipitation. If we go back to the article to table 1, we can see that the first variable to be created is the slope in degrees, and after creating the slope we need to reclassify it according to the table, assigning a higher weight, 5, to the lower slopes and the lowest weight to the steeper slopes. We assign a value of 5 to areas with lower slopes, as these are more prone to accumulating water. To create the slope, we need to go here to Analysis and click on this arrow. At the bottom, we click on More Tools. And here on the Geoprocessing toolbar, we need to search for slope. Click on this one. For the input raster will be the DEM. Output raster, click on the folder. I'll choose this one. Here I'm going to create two more folders. I already have this data folder where I keep my initial elements. I will also create one to store my intermediate data. I'll call this mid data. I'll save the slope here since it's one of the intermediate elements. Output measurement, it's degree as we saw on the article. Here, so the slope is on degree. In the parameters, we don't need to change anything else. And in environments, we are going to do the following. For the output coordinate system, we are going to choose the one with a map. So in this case, ETRS 1989 Portugal TM06. For the extent will be the DEM, not only for the slope, but for every element that we are going to create in the future. For the mask, we are going to choose DEM as well, and snap raster DEM as well for the slope and for all the elements that we are going to create. Let's click on Run. Here we have the slope. Going back to the article, we know that we now need to reclassify it, and we will use the same values as indicated there. First, actually, let me just read the short paragraph that explains why slope is used in this analysis. The slope affects the velocity in which the water is conveyed through the drainage channel and the watershed. Additionally, the steeper slopes, the higher the runoff will be, and consequently higher peak discharges will be generated. The slope layers was derived from the DEM, which is true, with a resolution of 5 by 5. 5 by 5 in this article, but in my case was 25 by 25 using the slope tool in ArcGIS in my case. It was reclassified in a scale from 1 to 5, where a value of 5 was given to lower slopes and 1 was given to higher values. Details are shown in the table 2. So now that's what we are going to do, reclassify the slope. Going back to ArcGIS Pro, we need to search for reclassify. The input raster will be the slope. Now if we go back to the article, we can see that below 10 degrees we'll have the value 5, between 10 and 20, 4, 20 and 30, the value 3, 30 and 50, the value 2, and above 50 degrees we'll have a value of 1. Let's click here on Classify. We need to change the method to natural breaks, for example. Change this to 5. The first one will be below 10 degrees and this one above 50 degrees. So we place 50 here, 30 here, 20 and 10. We click OK. So above 50 degrees we only have like 0.9. Click OK. And now we need to flip the values. So below 10 degrees the value will be 5. Between 10 and 20 will be 4. Between 20 and 30 the value will be 3. Between 30 and 50 the value 2, and above 50 will be the value 1. Click on Output Raster to save it. Since this is the final result for the slope, let's create another folder. So let's go to folders. Let's create another one, results, and inside the results folder I will save this as R, which means reclassify underscore slope. Click OK, and for the environment we do the same as we did before. So ETRS in the coordinate system, DN for the extent, and DM also for the mask and for the snap raster. Okay, so let's click run. And here we have our first result reclassified according to the article. Let's now remove this slope because we are not going to use it anymore. And maybe change the symbology. Let me just set the higher values to the red color and the lower values to a green color. So the value number 5 will be red. The value number 4, maybe this orange. The 3 will be yellow. The value number 2, maybe this green. And for value number 1, this darker green here. So as you can see, the majority of our study area has slopes in the class number 5 or 4. Slopes only start to appear as we move away from the coast. As you can see, if I place this base map, we see here the Atlantic Ocean. And as we go away from the ocean, the slopes tend to increase. Let me just rename this so we know that this is the first result. So 1R slope. Now we are going to calculate the height above the nearest drainage in meters. If we go to here, we know that the height above the nearest drainage has influence in flood susceptibility, since low-lying land adjacent to streams is more susceptible to be flooded than higher land. This map, in the case of this article, was generated with a previously developed tool by DILTS. In our case, this element will be made by us, meaning we will build the hand from scratch. But this requires the DM and the streams layers as inputs. And when reclassifying, lower values of hand were assigned to a higher class and higher values were assigned to a lower class, as shown in table number 2. Let's return to ArcGIS Pro, and in the geoprocessing toolbar we are going to search by the field for the field tool. For the input surface raster, we will choose the DEM. For the output surface raster, we will save this in our mid data, and I will call it fill, so we know which element is this one. For the environment, of course, we do the same as we did on the slope, and we are going to do this for all the elements that we are going to create in the future. Let's click run. So the next step, we need to go also to the geoprocessing toolbar and search for flow direction. For the input surface raster, we need to add the fill raster. Output flow direction raster will be saved also in the mid data, and I will call this f_direction. For the output drop raster and flow direction type, we don't need to change. And for the environments, we do the same as we did before. Click Run to generate the flow direction. Next, we are going to calculate the flow accumulation. So just search for flow accumulation. For the input flow direction raster, this will be the flow direction we create previously. And for the output location, this will be saved also in the metadata folder. So we just save the last result in the results folder, okay? So this will be called f underscore accumulation, but the name is too large. Let me set this a f ACC. Input weight raster, we don't need to add anything. Output data type will be float. Input flow direction type will be the same as we did before, so D8. And for the environments, we do the same. Let's click Run. It's important to understand that with these tools at this stage, we are extracting from the DM the likely locations where the water lines are situated. We can already see some of those water lines in this result. Now let's create a conditional if-else with the con tool. So let's click on this one. For the input conditional raster, this will be the flow accumulation. And then here we need to select or create a condition. We can see that in the flow accumulation we have values ranging from 0 to almost 660,000, and with this tool we are going to extract some of those values by applying a condition. The values we choose here depend greatly on the number of water lines we want to represent. Since I only want to show the most important water lines, I'll need to set a high value. But before that we are going to try several values so you can see the difference. So here let's try 500. Here we need to set this as the flow accumulation as well for the input through raster or constant value. We need to set a location. This is a metadata as well. Let me call this con, and we set the environments. I forgot to mention, but in the condition I set that I want to represent values greater than 500. Let's click Run. Okay, so we have our result, but we need to uncheck some of the elements so we can see better this example. Let me just invert the symbology of the con raster. Not here, but here. And let me just uncheck these elements. Okay, this one, also the census data. Yeah, we need to flip the values as well also, because now we cannot see because the rivers are represented in white. Okay, so here we have some of the rivers represented, but we have a lot of them, and I don't want this. I want to represent only the major lines. So we need to set a different value on the con raster. Okay, let me just add a base map so we can see if this actually represents water lines, which looks like it. If we increase the value on the con tool, we will end up with fewer water lines, keeping only those that represent the main ones. Let me remove the base map and increase the value from 500 to 1000 and see what happens. Let's click Run. We now have fewer water lines, but it's still not enough for what I want to represent. So we need to increase the number a little bit more. I'm going to set it to 10,000. From experience, I already know that this is a value close to what I need for this example. So let me just add a new 0 and click Run again. We can see that we have far fewer lines now, as we can see. Let me add a new base map as well. This time let me add this topographic, for example, so you can see better the water lines if they really correspond to rivers. Let me just wait a second and zoom in a location. If we notice, it's clear that these new raster aligns with the water lines shown on the base map. So let's proceed. Let me just remove the baseline, the base map once again. Let's now reclassify so that we have a single value to represent the water lines. So let's search for reclassify in the geoprocessing toolbar. The input raster will be the con. Reclass field will be the value. So let's click unique. Actually, no, we need to click on classify. Let's just wait a second. Let's click on classify. Let's change these to one class. Let me just repeat the process because it didn't work. So class will be one class. Okay, now it worked. Click OK, and the value could be value number 1. Okay. Output raster, this will be a mid data as well. So let me save this in the mid data. And for the name, let's call this R for reclassify and underscore con. Okay. Click OK and set the environments. After clicking run, we will have the rivers in one raster file. And finally, we now can calculate the height above the nearest drainage. Okay. For that, we will use the flow distance geoprocessing tool. So let me just go back, search for flow distance. The input will be the con we just create. The surface raster needs to be the fill. This one. Output raster, this will be saved on the mid data folder because the final result will be the reclassification of the height above the nearest drainage. So let's just save this in the mid data. Let me just call this hands. Click OK. Input flow direction raster, this will be the flow direction. This one. Distance type needs to be vertical for the hand. Remember that hand represents the vertical distance to the nearest water flow path. So we need to set this as vertical, okay? Set the environments as we did in the other results. And let's click OK to see the result. Finally, we need to reclassify the hand. Okay, so let's search for reclassify. Let's go back to the article actually. So values below 2 will have a class of 5 and values above 8 will have the class of 1. Notice that we have values between 0 and 506, and in the article we don't know the range of the hand. So we are going to use the same reclassification and values that we see on the article, okay? So we need to set these as 5 classes as we know, and we need to set these as the same with the same values as the article. Okay. So let's start, for example, with this one. Let me just adjust this a little bit first. So this will be below 2. This will be from 2 to 4, 4 to 5, or to 6 actually. The value number 4 will be from 6 to 8, and the value number 1 actually will be above 8. Okay, so from 8 to 506. Let's click OK, and the first value will have the class 5. Okay, so we need to flip the values. So here in ArcGIS Pro, this will be the value number 5, this will be 4, 3, 2, and this one will be the value number 1. So we have the hand reclassification with the same values of the article. Let's now save this result. This result will be saved on the results because it's the final step of the end classification. So r_hand, the reclassification of hand, and let's set the environments. Output coordinate system will be the same as current map. Extent will be the DEM, snap raster, and mask will be the DEM as well. So here, DEM here, and we can click run, and after the result is finished, we don't need, but I will change the colors so it matches the slope that we did previously. So the class number 5 will have the color red, so there's the more susceptibility to floods in the class number 5. Class number 4 will have an orange color, 3 with yellow, 2 with this light green, and lastly the value number 1 will have this dark green. Okay, so there we go, we have the hand classified. Okay, so next we need to set the distance to streams. Let me start by renaming the hand to be similar to the slope, and drag this to the bottom, maybe near. Actually, let me just remove this mid data because I think we are not going to use them anymore, or at least for the next results. Let me just drag this to the bottom of the slope, and now let's proceed to calculate the distance to streams. So, distance to streams. The measure of distance to stream plays an important role in defining areas susceptible to flooding. The zones closest to rivers are the most affected by floods. To obtain this distance, the Euclidean distance tool was used in the spatial analysis tool in ArcGIS. The reclassification was based on assigning a value of 5 to areas farthest from streams and the value of 1 to areas nearest streams, as shown in table number 2. To start, let's go to the geoprocessing toolbar and just search for distance accumulation. This one. By the way, I actually deleted that intermediate data earlier, but now I'm going to need it. So for the input raster or feature source, we are going to use the con. So let's go find it. This one, the reclassification of the con. Here, let's save this in the mid data as well. So let's call this maybe d_ACC, which means the distance accumulation. Click OK. We don't need input raster or feature barriers. For the surface raster, we will use the DEM, cost raster empty, in back direction empty as well, and let's choose the environments. Let's click run and wait for the result. So the green color represents the areas closest to the rivers, as we can see, while the more reddish and white tones indicate the areas that are further away. This one is pretty easy to do, so now let's reclassify the distance accumulation. Search for reclassify, drag the distance accumulation to the input raster, and let's click classify and look once again to the article so we can see which values we need to put here. So let's go back to the article. So the class number 5 will be below 100 and above 1000 will have a value of 1. Okay, so now let's place these values here. So this one will be 100, this one 300, this one I think it's 500, 1000, and the last one we don't need to change. Click OK, and we need to flip the value. So 0 to 100 will have the value number 5, as we can see here, and the value number 1 will have above 1000. Okay, this one will be 5, 4, 3, 2, and this one will be 1. Let's save this in the final result, and let's call it r_ds. Let's click OK, and once again change the environments. And we can also change the colors so it matches the hands and the slope. So remember, the 5 will have a color red. Number 4, we choose the orange one. 3 will be yellow. Not green but yellow. 2, this one is the green one. And lastly, the value number 1 will have this dark green. Okay, let me also rename this layer, remove this one, and and change the name to 3, drag this to the bottom of the hand, and the distance to streams is now finished. Next, we will create a raster using the curve number. As we can see in the article, this CN is an empirical parameter by the Soil Conservation Service used in hydrology for predicting direct runoff or infiltration from rainfall excess. It considers the characteristics of land use and soil type. The values of CN range from 100 for impermeable surfaces to 30 for very permeable soils with low runoff potential. The CN map was obtained using both the land use type data and soil type. CN values are published by the SCS for different land uses and soil types, as a high CN means high runoff and low infiltration, and a low CN means low runoff and high infiltration. High values of CN were assigned to a scale of 5, and low values were assigned a CN value of 1. So, as we saw at the beginning of this video, we already have the necessary base data. And as the next mentioned, we'll need to start by using the land use and soil type to assign the curve number values. Once we have that, we will reclassify the data according to table 2 from the article. As we saw in the text, the curve number is an empirical parameter developed by the Soil Conservation Service, So we'll start by visiting the SCS website. Just type Soil Conservation Service curve number and open that result, this one, from the Hydrologic Engineering Center. And if we scroll down, we can see some parameters. Under cover, we have the different types of land use, and on the right side, the so-called hydrologic soil groups ranging from A to D. The values shown are the curve numbers, which are assigned based on the intersection between these two sources of information. One important thing to note is that, obviously, when you apply this type of methodology, the land use categories you have won't exactly match the names shown here. So you'll need to adapt or approximate your data to fit your specific context. If we take a closer look to this shapefile, the soil hydrologic groups, I'll just activate the layer for visualization. We can see that there are gaps in the data. So we need to correct this, because if we don't, we will be introducing errors into our calculations. There are several ways to do this, but what we are going to do here is go to the geoprocessing tool and search for symmetrical difference. For the input features, we are going to drag and drop the soil hydrologic groups. For update features, we will use the land cover to fill the gaps. Let's save this into the MID data. Here on folders, flood risk using GIS and multi-criteria. Let's call this SAG SimDiff and click OK. Oh, I missed the folder. Let me just repeat the process. Here, click OK and set the environments. As you can see, what we did here was fill the blank spaces using the land cover data. But what we actually want is not the land cover itself. We want to assign a soil hydrologic group from B to D. So what we are going to do is assign to each land cover element the nearest soil hydrologic group using the near tool in the geoprocessing tool. So let's search for near, click on this one, choose the sim difference, the symmetrical difference as the input features, and near features we will use the soil hydrologic groups. After that, we only need to set the environments, in this case the extent as the DM, and what this tool will do is to create new fields in the attribute table of the symmetrical difference layer. These fields will include information such as the near feed, near distance, along with the attributes, in our case the hydrologic soil group, from the nearest polygon. We can actually open the attribute table of the symmetrical difference, so we see the result appearing in real time. So let me just click run, and we see that the table was updated. And if we move the scroll bar to the right, we can see that we have the near feed and also the near distance. So what we need to do now is to join this table using the soil hydrologic groups table and having as a common field the near feed from the symmetrical difference layer and the feed from the soil hydrologic groups layer. We can then perform a join operation. This will allow us to transfer the soil group information B to D from the nearest valid soil polygon to the land cover areas that we are missing data, so effectively filling the gaps with the closest valid classification. So let's use these elements in the join operation, feed here on the soil hydrologic groups. We can now click OK to perform this operation. And now, as you can see, we have the soil hydrologic groups in this symmetrical difference layer. Okay, Since we cannot proceed to any geoprocessing operation in a joined table, we need to export this joined table into a new feature. So let's right click and export data. Let's save this into the metadata folder. We can call this maybe something like SAG simdiff underscore join. Let's click OK. OK once again. The result of this layer is visually identical to the previous one, but as we can see, the attribute table is no longer based on a join. It has become a single standalone table. We can remove this one. If we open the attribute table, we can see that each row now has the value of the nearest soil hydrologic group. If we change, for example, the symbology and choose the field SAG_1, we can visually confirm a spatial relationship with the original soil hydrologic group's shapefile. Of course, the level of detail isn't perfect, but this is one of the valid approaches to help fill in the gaps and correct the error in the dataset, especially when you need a complete and continuous layer for further analysis. Next, what we need to do is combine the two elements, and for that we are going to use the merge tool. So just search for merge, this first one, select the soil hydrology groups and the SAG simdiff join, set an output folder, this will be metadata as well, SAG merge, and set environments. After that we click on the run button, and there we have our result. Let me remove this one. With the merge we can see that there are still blank areas, and I believe this is just a symbology issue, since after performing the merge, data got split across the columns. So let's check this. Let's open the attribute table of the SAG merge, and we can see the SAG, and if we sort ascending we can see that there are no values here. So we just need to transfer the values from one column that appears further to the right to this one, or from this column to the other using the field calculator. So we see that here we have the values, and right there at the left we didn't. So, and if we sort ascending, we don't have here but have on the other column. So we just need to use the field calculator and place these values on the other column. To do that, I will just select all the rows that don't have values in the SAG field. So I just select the first one, click Shift, and select the last one that don't have any values. Let me just see this one. Next, we right click on the SAG field. Here, click on Field Calculator or Calculate Field. And we just need to say that we want this selected column needs to have the values of SAG1. Okay, so because this here we have the values. So we just right click on SAG_1 and click Apply or OK to fill the data. There we go. This way we now have a fully populated SAG shapefile. We can even confirm this by double clicking the SAG field to sort the values. If there were any blank entries, they would appear at the top or bottom, but since none are showing up, we can be confident that all records are now complete. Let me just change the symbology again. Let me refresh, clicking on Add All Values. And there we go, we have all the values with the same color. This is now resolved, and now we are going to start assigning the curve number. To do that, we need to combine the land use and the soil type. We'll begin by searching for the intersect tool, which allows us to overlay these two layers and generate a new one that contains the combined attributes of both. This will be essential for assigning the correct CN values based on their intersection. So in the geoprocessing tool, just search for intersect. The input features will be the SAG merge and the land cover. And here the SAG merge. The output feature class. We can call it CN underscore classification, for example. Click OK and set the environments and click run. Here we have the result. Let me just remove a few elements because the project is getting quite heavy. So let me just remove this one. And here on CN classification, let's open the attribute table to see the intersection of these two elements. As we can see, we have the land cover information here, and further to the right we have the corresponding soil hydrologic group values here. The first thing we need to do to calculate the curve number is to create a new field in this shapefile where we will insert the CN values. Click on Add Field. I will call it CN. The type will be double and click Save. As I mentioned earlier, we need to match the original reference tables with the land use categories available in our dataset. In my case, I've already done that work in this Excel file. This Excel file will also be shared along with all the other data used in this project. As we already saw on the website, this is the structure of these tables, and if I go to the last sheet of this Excel file, we can see a direct correspondence with the data we are using. For example, for the areas classified as artificialized, I use the average curve number values from the category developed urban areas. For example, we can see that for cork, home and home oak, eucalyptus and maritime pine, I use the woods type. For the other broadleaf trees, woods as well. Shrubland, I use the brush. So I try to assign the values that best match my data. I'm going to place the Excel file side by side with ArcGIS Pro, and we will start filling in the field we created earlier with the appropriate curve number values. To do that, in Map, we go to Selection and click Select by Attributes, Add Clause, and let's start with land cover is equal to artificialized. Add clause again, then we say hands, and now we need to select the SAG file. So here select the SAG underscore 1. Actually, it's not this one, but the SAG, only because the SAG1 doesn't have all the values. So it's this one, and we can start with the B and click Apply. What this does is select only the records where this expression is true, in this case artificialized land with SAG value B. It gave an error because I had add to the current selection set as the selection type, but I need to change it to new selection. So let's change it here. And let's click apply now, and now it should work. Actually, let me just remove this. And let's click apply, and now it should work. I'm going to click this button here to display only the selected features. And as you can see, only the elements with land type artificialized and SAGB are currently selected. To enter the value, right-click on the name of the column at the top, and then select Calculate Field. And as we can see here in the Excel file, the value of artificialized with SAG type B, it's 81. So here on the calculate field, Cn needs to be equal to 81. And click apply. Now we do the same for the C type. So change this to C. Click apply. The C type is 87. So change the Cn value from 81 to 87 and click apply. And finally, the last one, it's the D. And this one has the value of 89. Click apply. We now have all the artificialized areas filled in, and we need to repeat this process for all the other entries in our table. Since this is a very repetitive task, I'm going to move on to the next phase of the workflow. Now that we have all the values in the table, I'm just going to represent them on the map by changing the symbology. So here we have all the Cn values. Let me just close the table and change the symbology of this shapefile. Right click on the shapefile and click on symbology. Let me change the field type from land cover to the last one, the Cn. Here on color scheme, I will select format color scheme, and right at the back, I will just select, I think it's continuous color scheme. This one will be pink and this one will be blue. And let's click OK. So the lower values will have the pink color and the higher values will have a more bluish color. Obviously, this type of analysis must always be done in a raster format, so we now need to convert this shapefile into a raster file. So in the geoprocessing, just search for polygon to raster. Click on this first one, drag and drop the Cn classification into the input features. The value field will be the Cn. Let's select the output. This will be saved in the mid data as well. Here. And we can call it, for example, Cn underscore raster. Here, let's click OK. Here we don't need to change, priority field will be none, and here we need to select the cell size. In this example, this will be 25. Since we are using the DEM as both the mask and snap raster, and the pixel size of that DEM is 25 meters, I'm going to enter 25 in this field to match the resolution. We set the environments and click Run. There we go. Let me just remove the shapefile. So let me just remove this file here. And there we go. We have the Cn raster here. So now if we go to the article once again, we now need to reclassify these values from 1 to 5. Okay. So as we can see here, the bigger Cn values will have a value of 5 and the lower will have a value of 1. In the example from the article, the range of values was narrower, going from 74 to 94, while in our case the values range from 58 to 100. However, by personal choice and to stay consistent with the original methodology, I will also use the same scale. So values below 74 will be assigned a class of 1, and values above 94 will have a value of 5. So going back to ArcGIS Pro, I will just search for the tool Reclassify once again. I will just drag and drop the CN raster as an input feature. So the first value will be below 74 and will be assigned a class of 1. So here let me just change this value to 1 to every number that is below 74. 74 will have the value of 1 as well. Now from 74 to 79 will be assigned, it will be assigned a value of 2. So these three numbers will have a value of 2. For the class number 3, it's 86, so from 79 to 86 will have the value of 3. Then from 86 to 90, in this case 91, this will have a value of 4. So the value 87, 88, 89, 90 and 91 will have the value of 4, and 94 and 100 will be 5. This will be, yes, this will be one of the final results. So this result will be saved in the results folder, and this will be called R_CN. Let's click on OK and set the environments and click Run. So here we have our result. To keep things consistent, I'm also going to change the symbology for this layer as well. So the class number 5 will have a red color. Number 4, it's orange. Yellow for number 3. And 2 and 1 will have green colors. Let me just remove this raster and drag the final CN result to the bottom of the distance to streams raster. Let me just also give this the number 4 to know that this is the element number 4. Let me drag this to the bottom. What comes next in the article is the calculation of total precipitation. At the beginning of the video, we saw an Excel table containing several meteorological stations along with their X and Y coordinates, monthly and yearly precipitation values, and at the end of the table, the average precipitation for each station between 2000 and 2025. This average value is what we'll be using next to spatially represent precipitation across our study area. We'll start by converting this table into a shapefile using the X and Y fields from the attribute table as the coordinate reference. So we just need to right-click in the total precipitation and select this Create Points from Table, XY Table to Point. Here on the Table to Point, as the input table, this will be the total precipitation.csv. Output feature class, this will be saved also in the metadata. We can call it something like, let me think, TP. Let's click OK. So the X field will be the X and the Y field will be the Y, and the coordinate system in this case will be WGS 1984. Since many of these stations are located outside our study area, we can go to the environment settings and define that we only want to include the stations within our study area. To do this, we can set our study area layer as the mask or extent, in this case the DEM, ensuring that only the relevant points are used in the analysis. So here on the processing extent, in the third symbol, we can set the DEM as the extent. Okay, so now only the points inside the DEM will be processed. So let's click OK and see the result. So let me see and zoom to layer. I think something went wrong. Let me see why. Let me open the attribute table to see if something went wrong. Maybe I did something wrong in the processing. So let me see. So we have zero results. Let me remove this and do the process again. So let me just go to create points from table again. And sometimes I think I know why this happened. Maybe the X and Y field are wrong. I will try to use the Y field in the X field and the X field in the Y field and see if this works. Let me click OK and let's see now. Okay, now it automatically worked. So let me zoom in the points and open the attribute table as well. And let's see. Okay, we have 4 stations in our study area. So what we need to do in this example, and if you are following the video, you need to swap the X and Y field. Okay, so let me just add labels to see the yearly precipitation, the average of the yearly precipitation. Let me check this one and click apply. And we can see that we have the lower values near the coast, near the coastline, and the higher values more to the center of the, or to the east of the study area. So how can we use this information in GIS? We can use the IDW tool. So go to the geoprocessing tool and search for IDW. It's this one. Let me just drag and drop the shapefile of the stations into the input features. In this case, the Z value field will be the total precipitation, the average of the total precipitation. Let me just save this in the mid data folder as well. We can call something like TP_IDW. As well, the cell size will be 25 meters. And we set the environments as well. And in this way, we have a spatial representation of total precipitation. Obviously, the more stations we have with data, the more reliable and accurate the result will be. Next, you already know what we need to do. We need to reclassify the IDW raster using the value ranges provided in this article. We can see already that the values are quite different. I mean, the highest value from the article is lower than my lowest value, so we need to do something to address this, which in fact isn't really a problem at all. It's just that we're dealing with different study areas and completely different datasets. To solve this, I'm going to use a simple reclassification method based on quantiles dividing the data into 5 classes. So clicking in Classify, I will change the method from manual interval to quantile. It's this one, and set the classes as 5. Let's just, okay, click OK. For the new values, we don't need to do anything, because if we go to the article once again, we can see that the lower total precipitation values will have a value of 1 and the higher values will be 5, which is what's happening here in this example. Okay. For the output raster, this will be saved in the results folder. So let's select the results folder. And we will call this R_TP for total precipitation. Click OK and set the environments, and then click Run again. So here we have the reclassified total precipitation data, and once again I'm going to adjust the symbology to better visualize the results. Now we can clearly see that what I said in the beginning of this step, it was true. The lower values are located more near to the coast, to the ocean, and the higher values are more located on the east side of the study area. Let's now move on to the effective precipitation. But first, it's important to understand what this is. If we do a quick search on Google, we can see that the effective precipitation is the amount of precipitation that is actually added and stored in the soil. It said also that during drier periods, less than 5 millimeters of daily rainfall will not be considered effective, as this amount of precipitation would likely evaporate from the surface before soaking into the ground. Effective precipitation enters the soil and becomes available to the plant. Effective precipitation is calculated based on an equation that requires both the total precipitation and the curve number values. I'm going to open the raster calculator tool, as you can see in the ArcGIS Pro, and explain the equation as we go. First, let's type float to tell raster calculator to return the final result as a floating point number, meaning it will preserve decimal values instead of rounding them. Next we type power. This means we are going to raise something to a power. In this case we're squaring a value, so the exponent will be 2. And next, since the original effective precipitation equation was developed using inches, we need to convert the units as we are working with millimeters. So inside the parentheses we just type TP_IDW and we subtract with the value 5080 and divide by the CN raster. Just do it like you are seeing on the screen. Next we close the parentheses and we do a sum with 50.80 and then close the parentheses again. To finish this part, we use a comma and then we do a 2. That will be the exponential value we talked earlier. Then we divide again, we open the parentheses again, 2 parentheses actually, we select the IDW again, and then we don't want to subtract, but we want to do a sum using this value and dividing by the curve number raster again. Then we close the parentheses and we do minus 203.2. I will try to remember to place this equation in the description below so you can use it. Let's save this in the MID_data folder. We can call this EP. And let's change the environments, and then we need to reclassify. We're facing the same issue as before. The values are quite different from those in the article, so once again we'll use the quantile method to reclassify the data. Okay? So let's open the Reclassify tool once again, drag and drop the effective precipitation as the input raster, click on Classify and choose the quantile using 5 classes. So the method will be quantile again, and the classes need to be 5. Once again, we don't need to change this the values, the class values in the reclassification because they are already sorted. We just need to set the output for this new raster. This will be actually the final result. So this will be saved on the final results folder, and we can call this r underscore EP. And let's click OK and set the environment one more time. Once again, let me just change the symbology to match the other results. And then we just need to set the floodplain as we saw earlier in the article. For the floodplain, the step is quite simple since we already have this data defined. All we need to do is convert the shapefile to a raster and then assign a value of 5 to the floodplain areas and a value of 2 to the areas outside the floodplain, as we saw in the article. So, as you can see in the map, this raster here, this shapefile here is the floodplain, and we need to start by converting this into a raster, okay? So let's search for this tool, polygon to raster, this one. Let me just drag and drop the floodplain as the input feature. The value field, it doesn't matter what you choose here. For the output raster dataset, this will be saved once again in the mid data folder. And I will name this something like FP. We need to change the cell size back to 25, so 25 meters. And once again, set the environments, the processing extent, and the snap raster, that will be the DM as well. Let's click run and see the result. Since we had 3 different values in the selected field, we're seeing 3 different colors here, but in this case that doesn't matter at all because we're about to reclassify everything in the same way anyway. So let's search once again for reclassify, and we can see once again, if we go to the article, that areas that are inside the floodplain will have the class of 5, and areas outside the floodplain will have the value 2. Okay, so just drag and drop the floodplain raster into the input raster, and we can see that the values 0, 1, and 2 will have the value 5 because are inside the floodplain, and here the value no data will be assigned a value of 2 as we saw in the article. Okay, so areas that has no data outside the floodplain will have the value 2. Let's save this into the results folder. This will be called r_fp, and the environment will be set as well. Let's also change the symbology of this new raster. The value number 5 will be assigned a color red, and the value 2 will be assigned this light green, as we did before. Okay, so here we only have 2 classes, 2 and 5, but there's no problem at all. Okay, let's set this as the value number 7 and drag this after the effective precipitation. And the first part of this article is already done. Let's compare my results with the results of the article. First, here we have the slope, then the hand, which looks similar, Then the distance to streams will look similar as well. Then the curve number. Then we have the total precipitation, which looks similar, and the effective precipitation, this one, and finally the floodplain raster. Next, if we scroll down in the article, we can see on this page how to calculate the hazard map under 4 different scenarios, each using a different combination of variables and weights. If we scroll down a bit further, we also see the need to create social and economic vulnerability maps using multiple variables. In the age indicators, we have people 75 years and older and children 4 years and younger. Family structure, we have lone parents. Language proficiency, non-English or French-speaking people, because in this case the article works with Toronto in Canada. Income, people with low income, education, high school education or less. Renters, rent apartments, and population density, in this case population density per square kilometers. Unfortunately for my study area, these data are not available, at least not at an appropriate scale, so I will be using only 3 variables instead. If we open the Census 2021 data, we can see the data that I'm going to use. We have the percentage of people above 65 years older and not 75. We also have persons under 14 and not 4, and we also have the percentage of rent apartments. So all these data were in absolute numbers, but I already convert to percentage. Then here in table 4 we have the vulnerability level that each indicator will be assigned from level 1 to level 5. Level 5 will be population over 80%, so in that subsection, if that indicator have more than 80%, will be assigned level 5, and if that indicator will have lowest than 20%, will be assigned a value of, or a level 1. In ArcGIS Pro, let's search for a tool. We need to transform this shapefile into a raster, so we will use again the polygon to raster tool. We can drag and drop the Census 2021 as the input feature, and for the value field we need to choose the 3 indicators we already saw. We can start with the rented apartments. We will save these in the mid data folder that we are using, this one. Let's try something like p underscore r APA for apartments. We need to change the cell size to 25 pixels as well and set the environments. We can already change for a new indicator. Let's choose percentage under 14. And since this is already set to the mid data folder, we can just change the name here in ArcGIS Pro. So we can call it R or P underscore U underscore 14 and click run, because all the other details will be the same. And we can do the same for percentage above 65. We only need to change here the name to P or to A underscore 65 and click run again. We can see that the values range from 0 to 100. For example, if we look at the raster representing the population over 65 years old, a value of 0 means that there are no people in that age group in that subsection, while a value of 100 means that 100% of the population living in that area is over 65 years old. Next, if we check the table number 4 again, we can see the criterion for each percentage and the assigned level. So we just need to reclassify these values to those in the table number 4. So let's search for reclassify. We can start with the rent apartments. The reclass field will be the value, and let's click classify, and let's change these values. So the level 1, or let's start with this one. So this will be lower than 80, then 100. This will be lower than 80. Then this one lower than 60, lower than 40, and lower than 20. Let's click OK. So if we check the article again, for the very low, needs to be below 20%, so will be this one. This will be number 2. 41 to 60 will be the class number 3. 60 to 80 number 4, and 80 or plus, or in this case 80 to 100 will be assigned a level 5. Let's save this in the results folder. We can call it R, which means reclassify, underscore R rented, and APA for apartments. Okay, click OK and set the environments. Before we change the symbology, let's reclassify the people under 14, for example. So let's drag this into the input features, and we just need to change the output name, because the classification will be also the same as the rent apartment. So we just need to change here the name and click run. These values will be the same for the people under 14, people above 65, and for the rented apartments, as we saw in the article. So let's click run as well here. Let's also remove this one, and let's finish with the people above 65. Change only the name. The classification stays the same again, and let's also click run. The environments are the same as well, so let's click run. While I change the symbology of these 3 new layers, notice that the reclassification for people under 14 doesn't include class 5. That's because the highest value we had was 65%, which makes sense. After all, it's very unlikely that children live alone in a given area. I'm going to finish this part by grouping these 3 results together and naming the output social vulnerability. Let's go back to the article. The next step will be to calculate the economic vulnerability, but since we don't have the necessary data for that analysis, I will skip this step. Here we have a table that shows the importance scale used in the AHP, the Analytic Hierarchy Process method, and there's a video explaining this method appearing right above, so you can check that video as well. In table number 10, we have the criteria defined for our elements across the 4 scenarios that we are going to represent. Let's begin with the calculation of flood hazard for scenario 1. I'm going to place ArcGIS Pro and the article side by side so we can more easily follow along with what's being done. I'll also remove some layers that I believe are no longer needed, just to keep the project clean and make the workflow smoother as we focus on building this first scenario. To combine multiple elements, we're going to use the raster calculator tool. So let's search for raster calculator. And for the first scenario, we are going to use the floodplain, the DS, the hand, the slope, and the curve number. So the floodplain will have a weight of 45%, so we open brackets. And let's double click on the floodplain. And then we need to multiply by 45%, so in this case 0.45. close parenthesis, plus open parenthesis as well. Then we double click on the distance to streams, which is the third one. Oh, I double click it twice and multiply by 0.22. And we just need to repeat this process for all the elements. The hand will be 0.13, as we see here. So hand, it's the number 2. Then multiply by 0.13 plus, and then the slope will have a weight of 12%. And finally, the curve number in this first scenario will have a weight of 8%. So 0.08. Let's save this folder in the results. So let's click on the folders here, this one, and let's call this first flood hazard result fh underscore scenario 1 s1. Click OK and set the environments. Here we have the first result, and we can see that the output ranges from 1.45 to 5, with 5 representing the highest hazard level. In a moment we will reclassify this result, but for now we can go ahead and change the color symbology just to get a clear visual understanding of what the output looks like. Remember that we assigned a 45% weight to the floodplain in this scenario, and that's clearly visible in the map, especially with the orange and red tones concentrated in that area. I'm not going to show the process for the other 3 scenarios since it's exactly the same as this one. The only thing that changes is the weight assigned to each variable. As you can see, we already have the 4 scenarios here just before reclassification. Each raster represents a different combination of variables and weights as defined in the article, and now we are ready to apply reclassification to standardize the outputs and assign meaningful hazard classes. So in the geoprocessing bar, let's search for reclassify. Let's start with the flood hazard scenario 1, the one I showed you, and let's click on classify, and we are still using the same method as we did before. That will be the quantile with 5 classes. So there we go. Let's set the environments here. The environments will always be the same. We will use the DEM for all for the accent, the mask, and the snap raster. And let's select an output to save this raster. Let's save this in the results as well, and we can call this r underscore fh underscore s1. And then we just do this for the scenario 2, 3, and 4 as well. So we just need to drag the scenario 2 to the input raster, like this. Click classify again and choose 5 classes using the quantile method. Click OK. Here just change the number 1 to number 2, since the output will be saved in the same folder. We just need to change the name slightly for the scenario 2 in this example. And we do this for the scenario number 3 and number 4. I went ahead and skipped forward since the process was exactly the same, and now we have the 4 scenarios fully reclassified. I will now just combine them into a group, and I will also change the color to each one of these results. This first map corresponds to the one shown here in the article. In the second scenario, we can see a prevalence of the distance to streams variable, just like in the article's map. In scenario number 3, we can clearly see that the curve number along with the effective precipitation become more dominant compared to the other less weighted variables. And in scenario 4, there is a greater emphasis on total precipitation. So we now have the 4 final hazard maps completed, which on their own already represent a time-consuming and fairly complex task. But let's take it a step further and move ahead to the calculation of risk, or at least part of it. As I mentioned before, in this example we'll be representing only a few social vulnerability variables, and economic vulnerability will be excluded from the calculation simply because I don't have the necessary data to include it in the analysis. Here in figure 7 of the article we can see that map A represents social vulnerability, and that's exactly what we're going to create now. In table 11 we can see the weights assigned to each social vulnerability variable according to the authors of the article. However, since I only have 3 of those variables available, I've adjusted the weights proportionally among them. For example, in the article the variable for older adults has a weight of 18%, but in my case I assign it 44%, young people received 41%, and rent apartments, which originally had 6%, now have a weight of 15%. Back in ArcGIS Pro, let's search for the tool raster calculator once again, just to merge or combine these 3 variables into one. So let's increase this here, and let's open parentheses, and we can start with rent apartments, which will have a percentage of 0.15. Then we sum with, for example, people under 14, which will have a weight of 41%. And then we need to sum again, and we need to finish with people above 65, which will have a weight of 44%. Okay, let's save this raster into a new folder. We can call this SV, which means social vulnerability, and we just need to set the environments, DM, and mask and snap raster DM as well, and let's click run to have the result. The lowest value of social vulnerability is 1, and the highest is 3.36. We'll now proceed to reclassify this layer. Although I believe the article does not explain exactly how this reclassification was done, I'm going to use the quantile method again, dividing the data into 5 classes. So just drag and drop the SV raster into the input raster, click classify, and just change the classes to 5 and the method from natural breaks to quantile. Click OK, set the environment, select the output folder and click run. I'm also going to change the color scheme for these rasters so we can better visualize the reclassified social vulnerability across the study area. Visually, it's immediately noticeable that the large green area, which you know corresponds to the floodplain, this floodplain consists mostly of rivers and water bodies, meaning there are no people living in these areas, which explains why they received the lowest vulnerability classification. In the article we see that there is a map of total vulnerability, but since we didn't create the economic vulnerability map, we won't be generating the total vulnerability map in this example. Finally, we're moving on to the final stage of this video, which is to create the flood risk map. Just like we did for the flood hazard map, we're going to calculate 4 different risk scenarios. To do this, we go again to more tools, and we will use raster calculator once again. According to the article, the risk is calculated by adding the hazard map to the total vulnerability map, or in our case the social vulnerability map, followed by dividing the result by the number of elements, which means a division by 2. Let me first select all the elements that I'm not going to use and remove from the project. So let's begin with map 1. Using the data from scenario 1, we'll combine the hazard map from scenario 1 with the social vulnerability map and then divide the result by 2 to calculate the final flood risk for this scenario. So first we select the social vulnerability, for example, and we will sum with the scenario number 1 of the flood hazard map. We then close parentheses and divide this result by 2. This way we continue to have a scale ranging from 1 to 5, maintaining the consistency with the previous classifications and making it easier to compare results across all the 4 scenarios. I will save this first result in the results folder and I will call this S1_risk_map. Let me click OK and change the environment once again. Let's click run and wait for the result. There we go, we have here the first result. For now I'm going to proceed with all the scenarios, and then at the end we compare them and we will change the colors also to compare them. Okay, so here I just need to change the flood hazard map with scenario number 2. So I just delete the scenario 1 and add the scenario 2. And here I just need to change the S1 to S2 because this will be saved in the same folder. So there we go. This is the result of the risk map number 1. Let's proceed to the risk map number 3. Okay, we just need to change the flood hazard map and also the name. And let's do the same for the scenario number 4. Click run. Okay, so now we have all the 4 scenarios. I'm now going to place ArcGIS Pro side by side with the article so we can compare our results with those of the others. So these are our final maps, and while we could go ahead and reclassify them following the same approach we've used so far in this case, since it's just for visualization purposes, I'll simply adjust the colors to make the results clearer and easier to interpret. So to sum this up, this was the methodology used in the article, which we followed and adapt to our own study area and available data. Throughout the video, we collect and process land use and soil data to calculate the curve number. We interpolated and reclassified the total precipitation and calculate the effective precipitation using the SCSCN method. We also derived topographic variables such as slope and height above the nearest drainage, the end, to better understand terrain influence. The floodplain layer was incorporated and all the variables were combined to generate 4 flood hazard scenarios. We then create a social vulnerability map using available indicators, and finally we combine both layers to produce 4 flood risk maps, matching the structure of the original article. All the data used in this project, from the initial inputs to the final results, will be available for download in the description of this video, so feel free to explore, adapt and apply this workflow to your own study area. Thanks for watching. Thank you for watching. If you like this type of content, don't forget to like, subscribe and comment what you want to learn next.